Welcome to Week 1, Lesson 1.1, Joint, Conditional, and the Two Laws That Run Everything. This is Part 1 of 8. Almost every finding in empirical finance is, once you strip the jargon away, a statement about how one random thing behaves once you know something else. Does next month's return depend on whether the market was calm or stormy? Does default risk depend on income? Each is a question about a conditional distribution. Nearly every tool you build, this camp, regression, causal inference, standard errors, is a way to estimate a conditional expectation and argue about how much to trust it. So we start at the bottom of the stack with two random quantities measured together. Here is the roadmap. We introduce joint, marginal, and conditional distributions. We define independence and conditional expectation carefully. Then we prove the two identities that quietly run everything later, the law of iterated expectations and the law of total variance. We anchor it all in a problem our trader Sam cares about, decomposing the variance of a momentum portfolio's return into the part from being in different market regimes and the part inside each regime. By the end, you can look at a messy source of risk and say, precisely, this much of the wobble is across regimes and this much is within. A random variable is a number whose value is not yet determined. We write random variables with capital letters, capital X and capital Y, and specific values with lowercase. Sam studies momentum, the tendency for recent price moves to extend over short horizons. Each trading day, Sam records two things. Capital Y is the market regime, one for a calm, low volatility day, two for a stormy, high volatility day. Capital X is the return on Sam's momentum portfolio that day in percent. The joint distribution of X and Y describes how the pair behaves, the probability of every combination of regime and return together. We pretend X is discrete, so the arithmetic stays visible. Everything generalizes to continuous X by replacing sums with integrals. A valid joint obeys two rules. Every entry is at least 0, and all entries sum to 1. Suppose Sam has enough history to estimate this table. Each cell is a joint probability, the chance the portfolio earns that return and the day is in that regime. The 6 cells add to 1, so this is a legitimate little universe. Read it like a map of co-occurrence. The calm roll under plus 2% is 0.30 on 30% of all days. The market is calm and the portfolio is up 2%. The stormy roll under minus 2% is 0.15. On 15% of days, it is stormy, and the portfolio is down 2%. Already the story's shape is visible. Gains cluster on calm days, losses cluster on stormy days. The rest of the lesson turns that impression into exact statements. To summarize Part 1, the joint distribution describes the pair of random variables together, one probability for every combination of return and regime, with all entries non-negative and summing to 1. Sam's table already whispers the real story. Gains cluster on calm days and losses on stormy days, which means the regime carries information about the return. In Part 2, we collapse the table into its margins and then make the central move of the whole subject, conditioning.